and welcome to the second episode in my series on computers, on Python programming, and on data science. In this video, we're going to try and jump from doing the hardware stuff that we were doing last time kind of into the digital realm. How does that happen? How do we go from specific hardware into something that we can program into and make the hardware do what we want it to do? So the first thing I have listed here is the fundamental component of any computer, of any phone device, of anything that's digital in our digital age, right? It's called a transistor. And at the fundamental level, its function is to turn on and off. It's like a switch, right? But it's a very small switch, right? We have the world's smallest transistor here is 1 nanometer from this image on Google's, right? And Intel's current technology they're working with is 14 nanometers. So the little tiny transistors and switches inside an Intel processor are as small as 14 nanometers. That's so small you can't even see it with your eye, right? You need a microscope to go see these things. And you're like, okay, well, we have a switch, right? We can turn it on and off. I know that. I've seen a switch happen in my physics class in high school, right? So how do we go from something that turns on and off into something that adds or something that does something that I've seen on a computer before, right? Well, it all starts very small and gets more complex as you go along. So kind of the next level step up from turning on and off would be a gate, right? It's called a logic gate. And so what we see here is that we have, two transistors that are located here that turn on and off. And we have some resistors in here as well, but they're, for the sake of this argument, they're not doing very much. And what we're going to get from this is we send in some signal A and we send in some signal B. And what we get out in the output, which they put here, this output is only going to be on if both A and B going into the system are both on as well. So you can see that the truth table is put down here. So when B going in is off and A going in is off, then you also get off when it goes out, right? And when B going in is off and A going in is on, then what you get out is off, and so on, right? So when we represent on and off for these transistors in computer theory or in electrical hardware theory, 0 is going to be off and 1 is going to be on. And you can imagine, off as there's no electrical current going through there, or the electrical current going through is so small that it can be counted as not going through at all, right? And 1 means the electricity going through is substantial enough that it can be counted as electricity is going through, right? So from the just on-off transistors that we saw, those switches that we saw in the first picture, we can generate logic as simple as, okay, 2 things are on, okay, 2 things are off, or vice versa, or maybe 1 thing's on and maybe 1 thing's off. That would be an OR gate, right? And so then from these tiny little logic gates, we can get even more complex, right? We can create a full adder, as they call it. And what this is going to do is going to add together A and B. So maybe if A is on and B is off, then that's going to be a 1 count, right? If both A and B are on, then that's going to be a 2 count, and so on. So how you generate this from this picture is you have an XOR gate, which is just like a gate we had before, or another XOR gate, an AND gate, and an OR gate, right? And from these together, we can create something that does math. That adds 2 things together. And so from this, you can generate a whole bunch of different, things that you need to actually generate something useful that a computer generates. So adding together is already something that's pretty useful. So now that we know how we can generate, circuitry to create what we want to do, we have to generate a whole bunch of different circuits that carry out these functions. So if I know that I want adding in my computer, I can take this exact circuit and create it in my circuit board, and I should be able to add, right? So that's exactly what they do with processors. They generate a whole bunch of different circuits like this that can perform a specific function, and they put it onto a circuit board. So that's what you can imagine that this processor has right here. And the processor that I'm going to show in this example, its only function that we're going to define is moving something. So we want the processor to move something from the hard drive into the RAM, right? It's going to be its only function. And so in English, what we can say is, okay, I want to move something from memory into something that's closer to the processor so that I can access it quicker next time. But that's something that isn't easily transferable, isn't easily translatable into something that the circuit designer has made, right? The circuit designer has maybe put in something that can move something from hard drive to RAM, but that's too complex just to spit in a whole sentence and expect it to have something generated out. So what we do is take that English version and convert it into something easy that someone can understand, but it's still kind of in between the two stages. And so what that's going to be is, something like x equals 2. So you could remember this from, maybe an algebra class, right? Is you're setting some variable equal to some number. And so maybe this sequence can only occur in RAM, right? So this is what potentially in Python language is how you would move something from your hard drive into RAM. Is you would set a variable called x and have the variable 2 brought in from the hard drive into the RAM so you can do some processing with it later. So we take something that was English, we convert it into something that's Python, which is a level, a little harder to understand for people, but easier for a machine to understand. And we need to take it another level down. So we'll call this right here Python. It's really just pseudocode. It could be almost any programming language. And we take that down one step into what they call assembly language. And so what this is going to look like is when I was not me specifically, say maybe when an Intel person was designing the processor for Intel, they decided on an instruction set that they wanted the processor to do, right? I was saying addition. That was probably one of the circuits they made and put into their processor. So they also put in something called a MOV command. So it would be spelled out MOV. So they have a circuit just like the one I did for the full adder that will take something from a hard drive and move it into RAM. And that command they called move, right? And so maybe they need to designate, the initial location and the final location. So maybe I want the initial location to be the first slot in the hard drive. Actually, I think here I have it listed as the second. So we'll put it as the second slot in the hard drive. So we'll represent that H2. And then we want to move it into the RAM. I guess we'll just call it the first slot, and we'll call that R1. So you can see that if I didn't know the instruction set, and I shouldn't have to know the instruction set of the processor of what someone else made, that I wouldn't know about this move command, right? I just kind of made that up. I understand x equals 2 completely, but MOV is just kind of nonsense if I hadn't heard of it before. So what the creator of this processor has done is made a compiler, is what that's called, that will convert this some language that someone can understand into whatever instruction set they've made in their machine. So together, Intel has done that. They've created an instruction set that's in every single one of their processors, and it's called x64 for a 64-bit machine. It's called x32 or x86 for a 32-bit machine. Or you could have like a phone, which would be running on, say, an ARM processor, which is a whole nother instruction set. So you could basically create your own processor if you want and create your own instruction set. Maybe it doesn't have a move command. Maybe it only has the add command in it, and you could call it, your own version of assembly. But the idea is that you need to be able to convert from this Python language that everyone understands into your instruction set, and that's where you would have some compiler in here. So the ability to transfer from some programming language into something that your hardware can understand is compilation. And it's a little misleading because Python is actually interpreted, so you can look up interpretation instead of compilation. But at some point, it goes through this process of being converted down into an instruction set. And so I'll just for the sake of sanity, how this looks is a whole bunch of zeros and ones that was shown up here in the truth tables, right? So when the creator of this processor came up with this instruction set called x64, they designed the move command, and what they did is they said, okay, to designate a move command, you need a identifier at the beginning, which is a certain number of transistors off and a certain number of transistors on. And so what's unique in the difference between this x64 and x86 is that 64 allows you to have 64 inputs into the processor. So there's 64 slots 64 transistors on or off that specify a command that this thing can do, right? So maybe the first, 20 of them are zeros, right? So the first 20 transistors for this move command, to designate that it's a move command, are going to be 0. Maybe if I wanted to do the add command, these first 4 that I have listed here might be 0, 0, 0, 1, right? So what you're going to see is the first 4, and it's not necessarily 4. For 64, maybe it's 20, maybe it's 30. There's a specifier that specifies what command to actually run on the processor. Now you're saying, well, what about these open slots over here? What are these designating? Well, depending on the command you have, you need the two what they're called parameters. And this first one I have listed here is the address of the initial location. And the second thing I have here is the address of the final location. So somewhere I need to specify those. So maybe they said, okay, well, the next 2 bits will be the of the initial location, the H2. So maybe H2 is represented 1, 0. And then maybe the final location, R1, is specified as 0, 1. These are just arbitrary, I made up. And this is something that the creator of the processor has done when they created the language. And so now you can see here that I have 1, 2, 3, 4, 5, 6, 7, 8 slots, right? All 8 of these slots get shoved into the processor at the same time, and that generates the calculation that it needs to do. So depending on how many instruction sets there are in the hardware, I can do unique things and make it do those unique things just based off on and off. And so now that we're able to bring something from the digital realm to where I wanted to set something to 2, and I made that into x equals 2, which is like an algebraic phrase, and then made that algebraic phrase into assembly, which is something that an electrical engineer has made into the design, finally into the just on and off sequence that hardware can understand, we now have a full functioning program, right? We move something from the hard drive into RAM. And if we can do that, imagine all the things that we're going to be able to do in the future. And I'll show those in future videos. So thank you so much for watching. Hope that if you have any questions, go ahead and leave them a comment, and I'll try and answer them as best I can. Hopefully that was clear enough. See you in the next video.